Okay. Okay. I want to start off with. You need a copy here. So I want to start off with just a basic example with where you're at right now. Raj, you're sitting in your chair. How fast are you moving? Well, depends. The Earth is moving. The Earth is rotating. The Earth is moving. So it kind of depends on your perspective, right? Even though it doesn't feel like you're moving, technically you are moving in comparison to other things. Let me give you another example. I'm driving in my car and I'm sitting next to Raj. Compared to Raj, am I moving? Well, no, because we're both in the car. But what happens if Raj is standing on the side of the road? Then am I moving? Yeah. Then I'd be moving way faster than him. What happens if a car goes by me at a faster speed? Am I moving compared to them at the same speed? Does that concept make sense? What I want to go for today is the idea of relative motion. The speed you have really depends on who you're comparing to. Right now, compared to each other, none of us are moving. But compared to Jupiter, all of us are moving. Does that make sense? Because the Earth itself is moving. Here's the example in my notes. Let's say that you are on a train and the train is going forward at 40 miles per hour. And you walk backwards on the train at 10 miles per hour. Compared to everybody else on the train, you seem to be going 10 miles per hour backwards. Does that make sense? But if there was somebody on the side of the road who could like physically see through the train, how fast would it appear to them that you were going? Let me say that one more time. So like if someone was standing outside of the train, looking through the train somehow, if the train is going 40 but you're going backwards at 10, how fast would it appear that you're going?
Not going.
30. Does that make sense? The train is going 40 that way, but you're going 10 that way. So to somebody on the outside, you'd appear to be going 30 miles per hour.
If you're going with it, would you be going
50, yeah. Does that make sense? So like if you were walking with the direction of the train, it would appear that you'd be going even faster. Does that concept make sense? Okay. The concept here basically is it depends on whose perspective you're coming from. Okay? If your perspective is on the train, the person walking on the train is also going the same speed as the train, so that 30 miles an hour is really irrelevant. Oh, perfect. Okay. But if you're off of the train, then the speed of the train itself matters. So if you're going against the train, it would be 30 miles per hour. If you're going with the train, it would be 50. And so this kind of puts in some weird examples. I'm going to fast forward in our notes here to one really far down the future here. I don't want to solve it yet, but I just want to talk about the idea. Suppose you are flying a fighter jet, which is currently going 25 meters per second, and then you fire a missile with an initial speed of 17 meters per second. How fast is that missile going? Well, it depends on who we're talking about. Compared to you in the plane, the missile is going 17 meters per second. But compared to like a person on the ground, you were going 25 meters per second. The missile is going an extra 17 meters per second. So then like a person on the ground would see the missile going 42 meters per second. Does that concept make sense? And so like the idea here could be that like if you're moving and you shoot something, the thing you shoot is actually going faster than it normally would go. Does that make sense? So like we could do all sorts of weird examples. You're riding on a train and you shoot a gun forward. The bullet speed would be even faster than it normally would be. Does that make sense? Or you're on a train and you shoot a gun backwards, the bullet speed would then actually be slower than it normally is.
Why wouldn't it say the same?
Well, because the bullet, like you are traveling this way, and then the bullet is traveling this way. And so like the fact that you were already traveling this direction would cause the bullet to almost like not move anymore. Oh, okay, that's still good. Does that make sense? Let me go back to the train diagram here. Let's say this was a really long train, okay? And the train was going this way at 40 miles per hour. And let's say you were capable of running backwards at 40 miles per hour on the train. I don't know if this makes sense, but the train would be running really fast this way. You'd be running really fast this way on the train. To the person standing off to the side watching you do this, it would appear to them as though you're not moving at all.
Is it kind of like,
Because you would just keep staying in the same spot. It would be like running on a treadmill almost.
Is it kind of like, you know, when you like walk up, down escalators? Like if you go faster than
Okay.
the escalator,
That could work, same
then
concept.
you're going.
Yeah, can we use a moving sidewalk instead? Do you guys know like how a moving sidewalk works in like an airport where, you know, it's basically like an escalator but flat, right? If you were just, okay, I need you full attention, okay? If you were standing on the moving sidewalk and just standing still, you'd move, right? If you walked with the moving sidewalk, you'd go past everybody who's standing still. But if you were a person who for some reason was walking the wrong way on the moving sidewalk, it would be like walking on a treadmill, right? And would you actually move? Well, compared to people standing off the sidewalk, no, you wouldn't be moving. But compared to people who were on the sidewalk, actually, you'd be going the wrong way. Does that make sense? So my point today is it's all relative. Depends on who you're talking about and where they're located. So, okay, that's the slide I had there. The term I want you guys to know is called a frame of reference. We have to know who is doing the observing. I found this cartoon. I hope this kind of makes sense. This person here says, "Wait, hold still," because to them the person's moving. But this guy here says, "I'm standing still," because technically they are standing still, right? This person's frame of reference is that they're not moving at all, but this person's frame of reference is that the person on the car is moving. I hope that concept makes sense. It's also known as an inertial frame of reference, if you ever hear that term. So my goal today is to solve a lot of different problems where your frame of reference could be changed. Here's a typical one. You're driving in a boat, and your boat is capable of going 1 meter per second. Okay. That's like the top speed of your boat. Okay. But there's a 1.5 meter per second current traveling down speed. So we can almost start making some diagrams like we did last day where you could have gone 1 meter per second this way. The boat is going to get carried 1.5 meters per second that way. Are you actually going to go in a straight line? Does that make sense? Now, what is your apparent speed? Well, to you, you would appear to be going 1 meter per second. Because like if you were in the boat and you were looking at your speedometer on the boat, it would say I'm driving 1 meter per second. But because of the fact that the water is pushing you, we could find your actual speed by calculating the hypotenuse right here. Do you guys remember how to calculate a hypotenuse? Alright, so c squared would equal 1.5 squared plus 1 squared. That's a c, by the way. Some calculator here. Anybody get an answer for C? Yeah, I got 1.8 as well. Okay. So your relative speed would be 1.8 meters per second. You would think you're traveling 1 meter per second. Because based on where you are in the boat, that's what you... Does that make sense? But because of the fact that the water is pushing you slightly sideways, your relative speed would actually be 1.8 meters per second traveling across the hypotenuse. Does that make sense?
Like, kind of like, so if you're driving a car or something that's really windy out, you're going 50 kilometers an hour, the wind is pushing you down faster.
Okay, that one might be a little bit different in terms of how your car measures that, because I believe your car's speedometer would be based on how much your wheel rotation would be. And so your speedometer in the car probably would pick up the wind, if that makes sense. I don't think that the speedometer in your boat would pick it up, because it would just figure out your speed based on how fast your propeller is rotating. And that would have been, does that make sense what I'm saying there? So it just depends on how your speed gets measured on the device you're actually on.
So our apparent speed is the speed that the boat would down
So like
percent.
you would think that you were traveling 1 meter per second because that's how fast your boat can travel, right?
Current is actually pushing you
But-
at 0.8.
Yes, because of the fact that you're getting pushed downstream. Here you're actually getting 1.8 meters per second in terms of what your speed is there. Okay. Third question: if the river is 150 meters across, how long will the journey take? Now, here's where this gets kind of weird. Here's what not to do. You don't say, well, okay, your velocity is your distance over your time. So like time would be equal to distance divided by velocity. Here's not how you put those numbers in. You don't say, well, 150 meters is my distance, and I'm going 1.8 meters per second. That's the wrong number to use. Here's the reason why. The 1.8 meters per second would be, yeah, you are traveling across that diagonal right there. But the 150 meters across is over here. Does that make sense at all? So those numbers, they don't really go together. This would be like the across the river number. This would be the diagonal numbers here. So I can't use this value right here as a velocity with this value right here as a distance. That's not really compatible. Does that make sense? Because this is the speed that you're traveling across on a diagonal. But like from here to here is 150 meters. But as you go from here to here, it won't be 150 meters, it'll be like 200 meters. Does that make sense? The 150 is specifically straight across the river. But are you actually traveling straight across the river? The answer is no. So the 1.8 is the velocity you're traveling on the diagonal, but if you're traveling across the diagonal, is your distance still going to be 150 then? The answer is no. Well, you'll have traveled further, wouldn't you? Right? Now, I don't know exactly how far downstream you're getting carried, so I can't use the hypotenuse. So here's how we solve this. We pretend that there was no pushing you downstream. Okay? So like, if there was no river current pushing you downstream, you would have traveled 150 meters at 1 meter per second, and so it would take you 150 seconds. So like, I guess the point I'm trying to make here is that when you've got these like relative kind of things with each other, the distance you travel has to be the same direction as the velocity you travel. You can't pick this guy's velocity and this guy's distance. Does that make sense? Like they have to be compatible with each other. So like this would have been 1 meter per second north. This would have been 150 meters per second north, whereas this would have been 1.8 meters per second. I guess it would have been like northeast, right? Since this direction right here is not the same as this guy's direction right here, I can't actually put those units together. Does that concept make sense?
If you had like the distance of where you ended up,
We could.
okay.
Yeah, like if you said this was 150 and I knew that this right here was 300, then we could Pythagoras' theorem to find this distance, and then we could use that distance and the 1.8 together
Fine.
to find time. And that would also work. Brad? That also would be valid. You could have used SOHCAHTOA to maybe find this angle right here, and then use that angle to find this distance right here. That all would have been valid, but that doesn't make sense to spend that much time doing the work when I do have two numbers right here that are in the same direction, if that makes sense. So it would make more sense just to use the 1 meter per second and the 150 meters. But you guys both make a good point. We could find this distance right here somehow, but are you guys getting what I'm saying here? You have to use a distance and a velocity that are going the same way. Okay, let's try another example. This is more of a thought experiment than an actual do math example. I pulled some data off of, I think this was from WestJet. Question? Oh, you're just stretching. This was from WestJet. If you want to fly from Edmonton to Toronto, it typically takes 3 hours and 38 minutes. But if you want to fly back from Toronto to Edmonton, it takes 4 hours and 6 minutes. Why is there a difference? I mean, you're going the same distance. Let's assume that the plane, like, is going the same speed. I don't know why the plane would speed up going from Edmonton to Toronto, but like slow down the other way around. So my question is, why is one way faster than the other way? Anybody know? Well, but that doesn't talk about the actual length of time the plane is in the air for.
Are you going with the roll?
Close, kind of, yes. Did you have something to point out?
That when you're going from Toronto to Edmonton, going against the
Okay, that's actually a really good thought, but the problem is you were originally going the same speed as the Earth was anyways, if that makes sense. So that wouldn't actually affect you. Does that make sense? Like, let me give you a different example. The Earth is rotating, correct? If I were to jump up in the air and then land back down, did the Earth rotate under my feet as I was actually going in the air? And the reason is no,
The jet
because
stream.
both me and the Earth, we were already traveling anyways. Does that make sense? So the rotation is not quite the thing. You're kind of close on wind, but it's not really wind so much. Has anybody ever heard of what's called the jet streams? Yeah, there's jet streams that exist really, really high up in the altitude, like in the atmosphere, with wind currents, and they always travel the same direction. So like wind that's lower down is less predictable. Sometimes wind goes whatever way, but way up high, the westerly or the easterly jet stream is always traveling one direction. And I believe, if I get this right, if you had like a globe here and Edmonton was here and Toronto was here, the jet stream up in the northern part of the hemisphere goes this way, and then like in southern parts of the hemisphere goes this way. But if you're traveling like far north, it's actually faster to go from Edmonton to Toronto because like the jet stream is pushing you faster. Does that make sense? But when you go from Toronto to Edmonton, you're actually going directly into the jet stream, which would then slow you down. Does that concept make sense?
It's like with those bike racers.
Yeah, exactly, right? Like you don't want to have like a headwind coming into your face, right? But if you can find a way to draft behind the person behind you and get rid of like that wind coming in your face, it can speed you up. Okay, let's try some other examples here. Okay, one more, then we'll do a math example. Hypothetically, you're sitting in the back of a pickup truck and you throw a ball up in the air. It would then land right back with where you were, right? Like, I throw this up, it lands right here. But what happens if the pickup truck was moving? Well, if the pickup truck was moving, you were moving forward. The ball was moving forward. So if you were to throw a ball up in the air, straight up in the air in the back of a pickup truck that's moving, it would actually come right back down in front, like it would land back in your lap. Does that make sense? Well, it may seem weird, but you would not need to throw it forward to try to catch it. It would go up and it would come back down, and the reason is that this ball, when you threw it, was already traveling forward. And so it would continue to travel forward without you actually throwing it forward. So if you throw it straight up in the air, it actually would land back in your lap.
It's just completely straight up. Yeah, like
Does that make sense?
exactly.
If you threw it straight up in the air, it would land back in your lap. Okay, well, try a different example here. Let's say you were in an airplane, which is clearly traveling very fast. If you were to throw something up in the air, it would come right back down in your hand, wouldn't it? It wouldn't just all of a sudden go up in the air and then like fly backwards into your chest and hit you.
Well, what if you're standing on top of the plane though?
Okay, same thing. If you threw it up in the air, it would come right back down, with one exception though. Air resistance could be strong enough at that point to throw it slightly off. So like traveling at really big speeds, air resistance might throw it off.
Just like sliding.
Does that make sense at all?
Yeah.
Like I feel like if I started like booking it down the hallway and I threw my calculator.
Let's try it. Okay, let's try it. Sit on the
Don't
hallway.
throw your calculator.
Sorry guys, we're gonna go do an experiment down the hallway here. Bear with us.
Someone find something to throw. Don't throw it.
Right, that's okay.
It's not gonna hurt.
Okay.
The fastest person in this room.
Okay, let's actually do this on a smaller scale. still work, minus some wind resistance.
Drop my calculator in
Just individual. Okay, so let's try some examples now of questions. The math, by the way, we're not using any different formulas, but like the way we have to approach the problem might be slightly different. Here's an example. You're driving in your car at a speed of 50 kilometers an hour, and you accidentally dropped your iPhone out the window. Oh. You stop the car 6 seconds later. I tell you how high the window is above the ground. We want to figure out how far behind you is your cell phone. So let's make the assumption that when the cell phone falls and hits the ground, it just stops there. It doesn't like roll and tumble for a while. Go grab breakfast real quick. I'm going to draw a picture.
Even though it would technically roll.
It probably would roll a little bit, I bet.
Makes me feel better when
I love her.
Can one of you guys grab me a juice box, please?
Do you want apple?
Apple will work. Thank you. Okay, you can try, guys. Okay, so I've got a bit of a diagram going here. See whether this makes sense to you. Your car, at this moment right here, you drop your cell phone 1.4 meters. Okay? But in the meantime, as you drop your cell phone, you're going to keep going and you'll eventually stop 6 seconds later. That make sense? So eventually over here, you stop. Now, what happened to your cell phone though? As you dropped it, say the car then moved to right. Actually, I wonder if I could literally pick that up. Let's say the car moved to right here. The cell phone would still be traveling forward at 50 kilometers an hour, wouldn't it? So like, is the cell phone gonna fall right here? Or wouldn't the cell phone like kind of fall right here? Does that make sense what I'm suggesting there? The cell phone will keep traveling at 50 kilometers an hour and slowly but surely hit the ground. That makes sense? So here is not where the cell phone's going to land. The cell phone will land a little further up. And our goal is to figure out this distance right here. So first question I have for you, how long will it take for your cell phone to hit the ground? Did we figure out how long it'll take just alone for the cell phone to hit? Well, what do we know? We know acceleration would be 9.81 meters per second. We know the distance the cell phone would travel would be 1.4 meters.
from the window to the ground.
Because that's from the window to the ground. Then,
Good time.
But not.
well, but we're looking for the time it would take the cell phone to hit the ground, right? Because I'm going to be further past that.
What would the velocity initial be 0?
Ah, there we go. That's the one we need. The velocity initial would be 0 because I dropped the cell phone, right? So I need a formula that somehow relates these 4 variables. And we're going to try to figure out how long it would take the cell phone to hit the ground.
Yeah, and then you can just cancel the VI.
Yeah, this formula right here works really well. Okay. Some of you guys are a little ahead of me here. If this VI right here is equal to 0.
Hey.
Oh. Hello? Is that you guys talking there? Okay. If your velocity initial is equal to 0, you don't really need to use this whole section right here.
Hey. This is Shulk.
Hey, you guys can hear me. Is something wrong?
Good. Fantastic.
Okay. Did anybody manage to solve for time here? I'll just skip a step. What'd you get for time?
0.534.
Okay, so I get 2 sig digs, so let's call 0.53 seconds.
How did you? Oh, we have to use. Oh, okay.
But like, I'm just gonna write down 0.53. We'll use them all. Do I need to show that step? Maybe I should. 1.4 meters equals 1/2 of 9.81 meters per second squared times t squared. Divide by this stuff. And then square root it all. Is everyone okay with solving for time first? Okay, here's what I was hoping to make the point of. You and the cell phone were both then traveling forward for 0.53 seconds. Okay? After 0.53 seconds, you're still traveling forward. Where's the cell phone?
Around you.
On the ground. Does that make sense? So for 0.53 seconds, both of you guys are traveling forward. Does that make sense? So like when I walk down the hallway, the paper towel is still traveling forward. I am still traveling forward, but after that amount of time, now like in this example, the cell phone is now on the ground, and I've kept going. If I can do a visual here, I won't actually use my cell phone though. I'll use my ruler here, right? As I walk forward, I've let it go. I let go of this thing probably right here, if that makes sense. And then for 0.53 of a second, we both kept going. Okay. Now, in our example here, as a car, I kept driving. Does that make sense?
Yeah.
So how much longer did I actually drive for if I drove for a total of 6 seconds?
5.4 something.
What'd you do?
Subtract 6 from that.
Does that make sense? So let me try that visual one more time. Here's me and my cell phone. I am walking along. I drop my cell phone right here. Now it's on the ground. This is 0.53 seconds right here. I kept going for a while more. We want to figure out that distance. So
So your new time is that subtract that.
So my new time now, the time that I was traveling while the cell phone was on the ground, I'm just going to write this out. The time in which the cell phone was on the ground, but I was still driving, was 6 seconds minus 0.53 seconds. So no, that's not right. 5.47 seconds. Does that make sense? Okay, now the example I gave here, I kind of simplified it a little bit. How fast was I still traveling though? So if I have a time and I have a velocity, okay, technically I probably should try to figure out like velocity final as well, if that makes sense. So like, I didn't actually say when I started to apply the brakes. Does that make sense? Like I didn't say you started applying the brakes immediately, but
Let's just say that they like stop right.
yeah, can we go with that? Let's just say that like after 6 seconds they're like, oh no, I dropped my cell phone. Instant stop. Can we go with that? I know that's not how it would work, but to simplify things. 50 kilometers an hour multiplied by 1,000 meters in a kilometer multiplied by 3,600. No, and that'll be on the bottom, won't it? An hour for every 3,600 seconds. $50 times 1,000 divided by 3,600. I've got a speed of, let's call it an average speed of 13.88 meters per second. Obviously, he has to stop. Does that make sense? But let's just say that he can more or less stop on a dime, to make things simple. So the cell phone was on the ground for 5.47 seconds. I was traveling at this speed here. So 13.8 meters per second times by 5.47 seconds. That would tell me how many meters away I am. That makes sense? The premise I wanted you guys to have here, though, is the idea of the cell phone has been on the ground for half a second, which means that I have been driving then for 5.5 seconds with my cell phone on the ground. I haven't been driving for 6 seconds with my cell phone on the ground. I've only been driving for 5.5 seconds with my cell phone on the ground because the cell phone kept going forward. Does that make sense? Okay. Let me just grab an actual answer here. I got about 76 meters. 75.9 is what I got here.
Yeah.
That being said, this probably was not real to life because I probably should have given you like an acceleration amount or something because technically like you would have slowed down gradually, right? Like you wouldn't just hit the brakes on a dime and instantly stop. But I didn't want to add that to this question. Questions on that? Okay, let's try another one. Here's the fighter jet one. So you are in a fighter jet, 25 meters per second, and you shoot a missile with an initial speed of 17 meters per second. Let me just say this one more time. Compared to you in the plane, the missile is going 17 meters per second faster than you are. But compared to like a stationary person on the ground, how fast is the missile going? Yeah, 25 plus 17. Because I'm probably shooting it. Oh yeah, let's go forward. I figure most. Yeah, I figure most fighter jets probably fire missiles forward. Maybe.
They just drop them, don't they?
Well, like okay, that would be like a bomb. I think like a missile would be like a rocket that shoots, right? Yeah, I missed a second squared there. Thank you. Who said that, Nicole? Yeah, that should be meters per second squared. Okay, come back again, guys. I only got 20 minutes left. Okay. So my velocity initial then is going to be 25 plus 17 meters per second. I'm going to give you an acceleration because the missile is actually going to speed up, right? Like, I don't know if this makes sense if you watch a movie, right? But like, the missile doesn't keep going just the same speed as the fighter jet the whole time. Otherwise, it would be like, here's fighter jet, here's missile, and they're both traveling together. Like, wouldn't the fighter jet like basically be just slightly behind the missile the whole time? That doesn't make sense. No, that wouldn't be safe. Right? You want the missile to go further and further away from you, so it needs to speed up. 2 meters per second squared. What was that? Well, I guess in theory you could slow down too or divert or something, but if you kept going on a straight path, you want it to go away from you faster and faster, right? So. Okay, last thing here, we want to figure out time. I strongly feel like we've used this formula recently. Wow, snark here. Wow. Okay, this one's a bit different this time though. Distance is velocity initial time plus 1/2 at squared. Last time my velocity initial was 0. This time, yeah, which causes a problem.
Oh, quadratic one.
That's a 1/2, by the way. That didn't turn out all that well. So some of you guys are catching this right off the bat. I can't isolate for t because there's 2 t's left over. That makes sense? There's a t squared right here, and there's a t, normal t, right here. So if I can't isolate for t, I need to use the quadratic formula. Before I use the quadratic formula, though, I need my equation to be set up properly. It's not currently set up properly. What do I need to do? Yeah, I need the 800 on the other side. I need it to equal 0. Okay. At this point here, I'd be okay if you kind of left your units away for a while, because units kind of is going to get in the way now. So your equation would be this. 1/2 of 2, by the way, would just be 1. So 1t squared plus 42t minus 800. That's what I'm trying to solve. for those of you guys in my Math-1 class in grade 11 this afternoon, we could try to factor this too. We would be looking for numbers that add to give 42 and times to give negative 800.
That's gonna be a messed up number.
Yeah, so I'm thinking quadratic formula might work better. So, negative 42 plus or minus the square root of 42 squared minus 4 times 1 times negative 800 all over 2 times 1.
They're not gonna give you.
Under the square root, I've got a number of 4964. You're supposed to get two answers when you use the quadratic formula.
The negative one's extraneous.
Yeah, the negative ones, if you know the term extraneous, it doesn't make sense to have a negative answer in the context of this question. Like, I guess in theory, if we could roll time backwards somehow, I don't know how that works even. That wouldn't make sense. I got 14.2 seconds. If I do the other one, I'm sure it's going to be negative. Yeah, I got negative 56 for the other guy.
Well, that was just sense.
Yeah, you can't really go backwards, and like that doesn't make sense at all in this question, right? So, based on where we're at, then I would expect that it takes. I should check sig digs. Do I only get 2 sig digs?
Yeah.
2 sig digs. Oh, by the way, while talking about labs, I was pretty generous this first lab around in terms of not using units. But I'm going to expect going forward that if you write down a number, it needs to have a unit next to it. Like, always. I can think of very few examples where we should not have a unit next to a number. Okay? So make sure you please keep units everywhere. I think the one exception would be when you're using the quadratic formula here, I'm okay if you take units out, because that's going to get kind of messy. But please make sure you use units. Please make sure you watch sig digs. It's important.
Is that 56.2?
Yeah, I had negative 56.2278, but I guess it's irrelevant anyways. It was negative. Yeah, that doesn't make sense, right? Does that make sense, the extraneous concept? That, like, sometimes you get an answer that in theory we solved, we didn't make a mistake, but it just, going back to the original question, it just does not make sense. You can't have negative time. Questions? Last one. Hopefully I have enough time for this one here. So probably this is the most typical kind of question I'd ask you to solve. You're a plane that needs to travel 300 kilometers due west. Just going to draw a quick map here. North. You want to drive... That's a really ugly line. Let me try that again. I'll even use the straight line tool. There. You want to drive directly west. That was your goal. Okay, here's your problem. The wind is blowing north of west. Hey, Forster. Sure. 65 degrees north of west would be like that direction. Does that make sense? That's about 65 degrees north of west?
Yes.
Just want to make sure I have that. 65 degrees north of west. So if you were to aim your plane directly west and the wind was blowing this direction here, would you actually make it to the airfield? You would actually end up going like that. And you'd miss your destination entirely. Does that make sense? So if you're a pilot trying to fly here, would you actually intend to fly directly west? Or where would you intend to fly? Okay, so here's what you might do then. Let me just see if I can pick this up here. If you know that this little wind piece right here is going to push you off course, what you might want to do is compensate by aiming to go slightly downwards. Does that make sense? And if you aim to go downwards like this, then when the wind pushes you off course, you end up at your destination. So if I could, I'd like to just redraw this a little nicer because mine didn't turn out great. So just bear with me. I'll draw it a little bit better this time. I'll even use a ruler, like a straight line tool.
Oh, the little circle thing. Remember the tail and
Oh yeah, let me change that here. What can I do that actually I can draw an arrow with? Line. This guy right here will work. So if the wind is going to push me this way, I should aim to travel like this. Does that make sense? So I will intend to fly this way. The wind will push me this way, and then I will actually have traveled in a straight line. Does that make sense? Well, now this is exactly like what we did last day, isn't it? Where we've got this triangle and we need to solve for many other parts to it. The good news here is that this triangle is actually just two triangles. There's a triangle right here, and there is a triangle right here. Does that make sense? I'm gonna start labeling some of the things I'm looking for. This distance right here was 40 kilometers an hour. This guy right here. I'm actually okay with just leaving it where it's at right now. I don't actually need to convert anything just quite yet. Let's say that you were trying to travel your third 350 kilometers an hour in 2.25 hours. Let's say there was no wind whatsoever. How fast would you need your plane to travel if you took this and divided by this? Yeah, so 350 divided by 2.25. So 155.5.
yeah.
Okay, so like if there was no wind, you need to aim for this line here to be doing 155.5 kilometers per hour. We can actually work with velocities everywhere. That's okay. We don't actually have to convert to meters or work with time. I can say if this guy's got to be 40 and this guy here needs to be 155, my question basically is, what does this guy need to be? Okay. Now this may seem weird, but if this guy is in kilometers per hour and this guy is in kilometers per hour, like we're always talking per 1 hour. It's okay that we just work in kilometers per hour, not in kilometers. If you wanted to convert to kilometers, though, you could take this number right here and times by 2.25. You could take this number right here and times by 2.25 and get distance, which just means that this number right here would also have been times by 2.25. So I guess the point I'm trying to make here is we can work with velocities all the way through. We don't have to convert. Last thing I got to do then is plot my angles. This angle right here was 65 degrees. Because it was 65, because like from right here, this would have been north, south, west, east. Does that make sense? So this would be 65 degrees north of west. I want to start finding some values. So like I want to figure out, why don't we call this one y1? This one will be x1. This guy will be x2. And this guy will be y2. So down here, how can I find x1? Good. That is a good point. When we find y1, it is going to be the exact same as y2. Yeah. So cosine of 65 degrees would be the adjacent over the hypotenuse. Cos 65. Okay, I got 16.9 when I solved for x1. So when I solved for this x1 right here, I got this guy as 16.9. That would then be in kilometers per hour. if I want to solve for x2 then, how would I find x2 if this section right here is 16.9 and this bit here is 155.55? What did you say, Lisa? Yeah, let me see if this makes sense here. You are traveling 155 this way here. You kind of have the wind at your back though, don't you? Like slightly at your back? So if you need to travel 155 kilometers an hour, but you're going to pick up like 16.9 kilometers an hour of wind, then you don't actually have to travel that fast in this direction. This guy will be 155.55 minus 16.9. So you don't need to travel quite as fast in that direction as you normally thought you would. So I've got this guy here as being 138.65. Let me say that one more time. You need to travel 155.55 kilometers an hour. But the wind is kind of at your back. Does that make sense? Like it's not fully at your back, but you're kind of getting a push from the wind. So how much of a push from the wind did you actually get? Well, according to using cosine down here, I got that you have 16.9 kilometers an hour. Like of the 40, 16.9 of it actually was at your back. Therefore, you only actually need to travel 138.65. Okay, one more thing here. The wind is also going to push you off course to the north. So we're going to have to compensate by going off course to the south a little bit. So if I want to find y1, y1 would be equal to 40 times the sine of 65. Which I got as 36.25. So what's happened here is the wind is trying to push you 36 kilometers an hour north. So therefore you better drive over here 36.25 kilometers an hour south. Well, now I have everything I need. This length right here is 138. This length right here is 36. Can I find a hypotenuse? So last step, c squared would equal 36.25 plus 138.65 anybody get a c squared value? Yeah, I got 143 kilometers an hour when I was done. You guys get that as well? Oh, okay, that works too. I'm glad it worked two different ways. Anybody else manage to solve that as well? Okay, so here's what that means then. What should the plane's air velocity be? He should intend to travel this way at 143 kilometers an hour. So that if he intentionally flies this way right here, the wind pushes him back. I don't have time to do this, but it was a velocity, which means I also need to know an angle. Does that make sense? It would really help if I could say find this angle right here. Does that make sense? So like if you didn't actually solve for the angle, we should also do that by doing like a tan inverse, because I have to intentionally fly like slightly south. Okay. But I'm kind of running out of time for that, so. Does that make sense? Okay, real quick, because I have like 1 minute. Next week, we're going to do our last lesson of the unit on Monday, a lab on Tuesday, a work day Wednesday.